Let's get started on our new topic. We are going to be doing section 3.2, which I forgot to put here. And we're going to look at what are called the product and quotient rules. And right now we know one rule, it's called the power rule. That's the only rule we really know. And we've been using it a lot, multiply by the power and reduce the power by 1. And now we're going to look at is there a way to find the derivative of two things multiplied? And the answer is yes. There's a formula for it called the product rule. How about two things divided? Fractions, quite complicated fractions. And yep, there's a rule for that. It's called the quotient rule. And then there's a third rule, which is my rule. Just because you can doesn't mean you should rule. And what that means is that you're going to get some questions where you could use the product rule, but actually there'd be less work if you did some algebra first and then just differentiated in the usual old-fashioned way. So just to show you that that can and does happen, I've put that third rule in. There is no law that says you must use the product rule or you must use the quotient rule. In certain circumstances, it's the only way you can do it. I understand that, but it doesn't mean that you have to do it all the time. So let's look at the first one called the product rule. Now, if you have a function y equals, and it's made up of two functions multiplied together, f of x and g of x, right? So it could be anything. It could be x cubed e to the x, for instance, right? That would be an example of that. Or x squared plus 1 brackets x cubed minus 1, whatever, right? You can use the product rule. And the derivative, which I'll use that notation, is f dash g plus f g dashed. And it's a formula. You plug in the derivative here for f, you multiply that by the untouched g, you then add the untouched f and you multiply by the g, the derivative of g. So let's show you an example of that. I would like to know the slope of the tangent line to that curve at any value of x. Well, I can't use the product rule because, well, there's an e to the x there, right? Sorry, I can't use the change. Let's get this one. I cannot use the power rule because they're multiplied together. They're two things. So what you do is you identify who the f and the g are, and then you can do the formula f dashed x, g of x, plus f of x, g dashed of x. And if you differentiate x cubed, it's a power rule, you get 3x squared. If you leave that one alone, you still get e to the x. If you leave the first one alone, you get x cubed. And if you differentiate e to the x, you get e to the x. So step one would be this one, right? Identify who the f and g are going to be. And this here is really step 2. Use the formula, then you got your answer. There is a third step, step 3. Style points. Everything you do in derivatives, when you finish differentiating a function, the last thing you should look at are style points. And there are 3 rules for style points. Collect like terms together, factor the heck out of it, and make it look like the original. We've only used make it look like the original so far. Now we're entering product and quotient rule. We're going to have a lot more algebra to do. The calculus is probably going to be the easiest bit of the whole thing, right? Getting this answer. The hard part is going to be to make it look pretty. If you look at this expression here, is there a common factor? Because we can factor the heck out of it. I guess the question is, what is the common factor for these two terms?
X squared e to the x.
You all agree that's the common factor? Now, if you pull out, you got 3 here, and over here, you have an x. And this is the correct final answer. And I do not care what WebAssign accepts. WebAssign may accept that. I don't care if it accepts that. I want you to get into the habit of doing this, because this is going to be your friend, believe it or not, although it's a lot of hard work. It's the proper way that all mathematicians expect things to be written. That's just a simple rule. That way everybody writes the same. But it's more important than that. If you do this to it, you will be able to find what are called critical numbers. That are special values of x on a function where interesting things happen. I can look at this expression and I can tell you 2 different values of x where there's a 0 derivative. Now remember, 0 derivatives are horizontal tangent lines, and horizontal tangent lines tend to happen like here and here. And isn't it a good idea if you can find those places, because they're almost always the most important place in a curve. And in this case here, can you see that x equals 0 would make that happen? But here's one you might not have noticed. Won't x equal -3 also have a 0 derivative? Now, if you had left it like that, you probably could have guessed that x equals 0 was going to get you a 0 derivative, right? But if you left it like that, what's your chances that you would have figured out that -3 was going to work? Now, you could easily have missed that one. So I'm kind of trying to sell the idea that style points, although they're a pain and you have to do algebra and you have to do a lot more work, they are the way to go, right? You just have to get into the habit of, well, that's what I do, so that's what I do. Try another one. Suppose I gave you a function and I'll call it x squared plus 1, 2x squared plus 4x plus 7. And that is definitely a product rule. Would you agree it's 2 things multiplied together? Great. And now I'm going to call this guy f. I'm going to call this guy g. So its derivative, f dash g plus f of g dashed. Now, if you differentiate f, you get 2x, and you leave g alone. And then you leave f alone. And if you differentiate this guy, you get that ugly mess. Now, in this situation, the style points thing is going to be collect like terms, factor the heck out of it, and make it look like the original. Well, if I look at these terms, I'm not going to get any common factors. So what I'm going to have to do first is just multiply the whole thing out. Oops, that's a 4. So that times that is 4x cubed, 8x squared, 14x. This is going to be a FOIL, so that's going to get me 4x cubed plus 4x squared plus a 4x plus a 4. And in this case, it's going to be collect like terms. So what have I got? I got these 2 guys, and that's 8x cubed. I got this guy and this guy, so it's going to be 12x squared. We've got this fella and this fella, so it's going to get me 18x, and then add 4. Yeah, That's pretty much the end of the line for that. Technically speaking, I could have pulled out a 4. Oh, take that back. Best I can do is pull out a 2. And I don't think there's any real benefit. So leaving it as a polynomial would probably be fine. So far, so good. Let's look at a question that doesn't look like it's a product rule at all. Now, we know how to differentiate e to the x. The answer is e to the x. You might think e to the 2x will just have a derivative of e to the 2x. It'd be really nice if that was true, but it's not true. So we're going to find out what the derivative of e to the 2x is. I'm going to use the product rule.
We can separate them, right? Yeah.
Exactly. So now it's a product. So now I can use the product rule. The fact that f and g happen to be the same guy doesn't really matter. There's no reason why it has to be different. So now I'll do the derivative. So it's going to be f dashed g plus f of x, g dashed of x. And there's going to be an awful lot of weird, it's the same thing going on here. Because the derivative of f is still e to the x, the untouched g is still e to the x, the untouched f is e to the x, and the derivative of g is e to the x. And these two can now combine to give you e to the 2x, and these two combined to give you e to the 2x, and then you put them together, and there is your derivative, collecting like terms. So the derivative of e to the 2x is 2 times e to the 2x. What's your gut feeling for the derivative of e to the 10x? You might have caught it, but I didn't catch it. If you could say it again, please.
10e to the 10x.
Yeah. What would its derivative be?
That'd be the derivative.
It must be just a sound thing, or I'm just getting so old I can't hear you.
10e to the 10x.
Yeah, that might well have been what she was saying. It was just breaking up at my part. It might not be breaking. You lot might be hearing it perfectly clearly, and you're wondering what my problem is, but I wasn't picking it up. Yeah, it's 10e to the 10x. Can you see what mathematicians do when they see something? They say, oh, so the derivative of that is that. I wonder what the derivative of e to the 3x is. Well, couldn't you split e to the 3x as an e to the 2x times another e to the x? And you already know what the derivative of e to the 2x, so you could use that to help you. And then you do it 4 or 5 times, and you say, hey, there's a pattern here. I wonder if it's true all the time. Let's see what kind of things I can come up with here. Let's look at some of the homework questions. Give an idea of what they look like. Nothing special. Okay, let's try this one. This is like question 4 from the homework. So y is going to be x plus 9 square root of x e to the x. Let's kick back in. There we go. Now, this entire horrible mess is going to be F, and this little guy here is going to be G. So F dash G plus F of G dashed. It's got a nice symmetry to it. If you differentiate this guy, we probably need to do something about that. Maybe do it as a little side issue. I need to find the derivative of this guy, don't I? Now, you might have done enough that you can just do it in your head, but for those who, that's not, you're not there yet. Won't you have to call this 9x to the half? Now I can differentiate. I get a 1, multiplied by the power, reduce the power by 1, okay? So I got this guy now. Let's put him in here. The derivative, and leave G alone, plus leave F alone, and differentiate G. Now, if I, there are two ways of doing this. Let's go this way. Have you noticed that in this question, they both terms contain an e to the x? I can pull that as a common factor. That leaves me with some rather ugly pieces. Agreed? Now, 3 rules to style points. Collect like terms, factor the heck out of it, and make it look like the original. Is there a problem with the third one? Does this look like the original? Would you all agree that that's the guy that needs to be fixed? Right? This negative half guy. So it's not a big deal, but we want to do what we want to do. Right? We want to make it look like the original. It's not a pretty answer, but it's as good as it's going to get. You agree? Pretty ugly answer. But at least we factored it, right? Okay. Here is a function that qualifies under just because you can doesn't mean you should. Would you agree that is a product rule? At least it looks like it. This would be F, this guy would be G. And could I do the product rule? Yes. Would it be a bit ugly and take me some time? Definitely yes. So I could do it.
It's also a good square function.
So why don't I just do that? Do you know if you FOIL this out, can you trust me that's what you get? Have you done enough things with its conjugate, right? Difference of 2 squares, whatever you want to call it. Agreed? Now that I've written it like that, isn't its derivative dead easy? Now, if I left it as F times G, right, and, you know, did the product rule, right, all of this, I would have got a whole load of ugly terms times another whole load of ugly terms. And then there would have been like carnage where everything killed each other off and all that you would end up with was 2x minus 1. You'll still get the right answer, but you would have taken the scenic route. And if you're wondering where this phrase, because it's obviously made up by me, just because you can doesn't mean you should rule, came from, when I was young, I used to sing in the shower, still do, right? But you got to know, I can't sing to save myself. And when I was young, my mum used to bang on the door and she would say something like, just because you can sing doesn't mean you should, right? So just because I could do it, it's not always a good idea, right? That's probably a good piece of advice for life as well, isn't it? Just because you can do something doesn't mean you should. Don't know where I'm going with that. Oh, might as well. My brain's working on it. I was a very, very boring student. I never took drugs, was never interested in drugs. I had friends who actually took drugs, and they used to say things like, "Why don't you take drugs?" I said, "I don't want to. Not interested in them." And they said, "Well, you don't know how good it is unless you've tried." You know, that stupid argument. I never did try. And I used to say to them, you know, I've never banged my head off a wall, but I know it hurts. Right? So if you've got idiot friends who are trying to get you to do stupid things, well, you remember just because you can doesn't mean you should roll, because it applies to calculus and it applies to life. So there's my little moral story of the day. I think I'm too old now to start taking drugs. I mean, I've got through my entire life without doing it. I think I should be okay. Well, who knows? There, but for the grace of God, go I. Anything interesting? I'm just trying to find some that are a little bit weird. Ah, this one looks interesting. We're going to do, this is like 17. So it's y is going to be e to the p plus p square root of p. Now, this one is not one of the step 3s. This is a product rule. The problem with this guy is that it's not quite ready to have the product rule done to it. Is there anything here that you can see that probably should be fixed before I start differentiating anything?
Square root.
Right. In fact, the p and the square root, you know, this combination here. Now, the best way to take care of this would just be to realize that you can call that p to the 1 and p to the half. And if you put them together, there. So p square root of p can just be called p to the 3 halves. Wouldn't that be much easier to differentiate now? Don't think of that as a product rule or a little baby product rule. I mean, to be honest, you'd still get the right answer, but wouldn't it get messy and ugly and just bigger than it needs to be? You know, take the simple root if there is one. Call it that. Right, now we're ready to differentiate. F dash g plus f of g dash. Tell you what, can I stop putting the x's and p's in now? Can I write the product rule like that and you all know what I'm talking about? I mean, it's not much, but you cool with that? I don't need to put in f dash p, g of p plus f of p, g dash of p. You know, it's just a shortcut way of writing the formula. Okay. Well, I guess I should put my little labels. Your f and this whole thing is g. Right, so if you differentiate this, you just get e to the p and you leave this fella here alone. And you leave this guy alone and you differentiate this. Well, that guy gets you 1 and this guy gets you 3 upon 2 p to the half. Ah, I think I know how this one's going to finish. Right, let's do style points. What would be the easiest thing to do in this expression here to try and make it look pretty?
You wanna
the e to the p.
Okay, I think you want to factor and someone else said e to the p. So between the two of you, I agree. You do not need the next line, but I'm a picture straightener. Things annoy me. What did I just do there? I mean, this answer is totally correct, but what did I do in my picture straightening format in my brain?
Put them in order of the powers.
Yeah. I mean, x squared plus 2x plus 1, in my brain just looks right. Would you agree 1 plus x squared plus 2x is correct, right? It's the same expression, but doesn't it just kind of jar on your brain? Or probably just jars on my brain. Do I like the product rule? Do you feel comfortable about it? It's basically two things multiplied together, and you do the F dash, then you do the G, and off you go and make it look pretty. I think I'll do one last one, and then we'll look at some quotient rule ones. Okay, that's the guy that we're going to find the derivative of. Is there anything I can do to help on the process? Is anything in that expression that really needs to be changed before I start differentiating?
The square root of z needs to be changed.
You all agree that square roots aren't really very helpful when you want to differentiate, so we'll turn into a fractional power. When you do the same thing, if it was a cube root or some other radical like that, you would turn it into a fractional power. Now, in this case, the derivative then is going to be f dash g plus f of g dashed. Call this f, the whole thing. Call this guy g. Right, let's see what we get. If you differentiate this, it's multiply by the power, reduce it by 1. If you differentiate this guy, you get e to the z. Okay, that's good. And then you leave this guy alone. It's z to the half. Plus, if you leave this guy alone, and if you differentiate this, you get 1/2 z to negative a half. Now, I know they're both powers of z, but they're not common, right? That's a negative a half, and this is a plus half, so that really doesn't work. If I just distribute this, oh, do I want to distribute it? Yeah, I guess I do. I'm seeing if I can get anything at all out of this. And the only thing I can see, but maybe you'll see something I'm missing, so minus a half there, is that this guy and this guy can be added together. Okay, I'm kind of running short of room here. Is that a good answer, or could I make it prettier? I've collected like terms, not that there was much going on that way, but I did. These two give you 6.5, which is 13 halves. But isn't there a make it look like the original rule? And did the original have half powers in it? No. So what you want to do here, actually, this one here is a bit weird looking, because eventually it looks like that when you take care of it. Right, that last one, this third term, is the weirdest looking. What can I tell from this function? Well, there's not a lot I can tell, except isn't z equals 0 a bad idea? If you had z equals 0, won't this term here be 1 over a 0? So this function, whatever this function is, something bad is happening at z equals 0. I suspect it's like the side of a circle. I think it's coming down vertical. I'd have to look at it and see in Desmos. Okay, let's look at the quotient rule. The quotient rule's really how you differentiate fractions, how you differentiate something on the top being divided by something on the bottom. Quotient's just an old name for fraction. So suppose you have a function that's written like that. Then you can get its derivative by using this rule, the quotient rule. It's f dash g take away f of g dashed all over g of x squared. Now it's a much uglier looking function than the product rule. You agree it's a pretty ugly looking function. So let's do an example. We'll keep it simple. X squared plus 1 over 4x minus 2. We wouldn't be able to differentiate that using the power rule. There's no real algebra you can use to break this apart, you know, in some way or other and use a power rule on it. We just couldn't do it. The only way we can do a question like this is by applying the quotient rule. Well, step 1 is to identify the f and the g. I don't think that's a big problem, right? F all on the top, right? G is always on the bottom. Step 1. And the formula. Can I do the abbreviated version of it? Right. Let's see what all the pieces are. If you differentiate the top, you get 2x multiplied by leave the bottom alone. Take away, leave the top alone and differentiate the bottom. And then whatever is in the bottom, square it. So that's us basically applied the quotient rule. F dash g take away f of g dashed. What do you think I'm going to do to the numerator in this answer? I'm not going to leave it like that. What am I going to do?
Expand it.
Distribute.
Distribute. That times that, ax squared, that times that, negative 4x. Be careful about that subtraction because you're subtracting both things. So 4 times x is take away 4x squared, and 4 times that is take away 4. And now I can collect some like terms, and I have a 4x squared, a negative 4x, and a negative 1, negative 4 I should say. Now, in this particular question, we should try and factor the heck out of it. Would you agree that I could pull out a common factor of 4, but that's probably not going to do much. So if it doesn't really do much, I'm not bothered if I don't do it. I should try and see if I can factor it because it is a quadratic. Can you trust me? It doesn't factor. So that's the end of the line. But will you be on the lookout for quadratics, especially? Because couldn't you imagine a different question where that did factor, right? As 4x plus 1, x minus 2, you know, that kind of thing. And if that is possible, then that should be done because we've just done collect like terms. Shouldn't we factor the heck out of it and then make it look like the original? I don't need to worry about making look like the original, right? That kind of happens by accident. But shouldn't I think seriously anyway about collecting like terms and then factoring if possible? Try this fella. A nice fraction. Call the top guy F. Call the bottom guy G. Use the quotient. F dash G, take away F of G dashed over G squared. Okay, if you differentiate the top, you get e to the x plus 1. If you leave the bottom alone, you get that. Subtract, leave the top alone, and differentiate by the bottom. And then square the bottom. Foil out, foil out. Okay, e to the x times e to the x is e to the 2x. E to the x times that gets you this guy, plus 1 times that gets you this guy, plus 1 times that guy gets you negative x. Now, you're then going to subtract this guy foiling. So I'm going to foil this and then remember to subtract each term as I do it. So e to the x times e to the x is e to the 2x, and then I subtract it. E to the x times this is negative e to the x, but then you subtract it. X times that, and then you subtract it. And lastly, x times negative 1 is negative x, but then you subtract it. Okay, with a bit of luck, there should be some major carnage going on here. Right, let's see who gets killed. Would you agree e to the 2x gets killed? On. Anything else in that list that's going to die?
X.
Okay. Anything else in this list going to die? Or is that it? That's it. So let's see what we get. One of these and one of these gets me 2x e to the x. One of these and one of these gets me 2 e to the x. Hopefully I didn't do anything wrong there. Style points. I can do some more. Anything that you can do to that top that would make it look better in the style point world.
Factor out an e to the x.
Correct. Anything more?
Also a 2.
Now, what does that leave me with? Technically, a negative x plus a 1. Agreed. And you don't need this line. I like this line. I mean, doesn't 1 minus x just look right? I mean, mathematically, it's you're never going to get dinged for it, really, but it just looks right. Straighten the picture, right? Make it look pretty. But technically speaking, in a test, I'm not taking points off. I say that you're right. Let's look at this answer for a minute. Would you agree that at x equals 1, this derivative is going to be 0? Agree? And at x equals 1, there's probably a top of a hill or a bottom of a valley going on. There is a third possibility called the horizontal point of inflection, but they're pretty rare. So it's mostly a hill or a valley. So I'm kind of interested in how that might happen. And the fact that I've done this allows me to do that. Okay, let's do an example of a just because you can doesn't mean you should drill. here is a fraction, and fractions are quotient rules. I don't really want to do the top the way it is and the bottom the way it is, and I could, and it would work. But there are other alternates. Could I make this fraction look prettier and then do a quotient rule on the pretty version? And the reason I'm saying could make it look prettier, can you imagine that all these 1 over x's are just going to be a real pain when you have them all over the place, and then you're trying to collect like terms and just generally working with it? So why don't I multiply top and bottom by x? And what does that get me? It gets me x squared plus 1 over x squared minus 1. Now, this guy is mathematically equivalent to the original. Would you agree that this guy is going to be really nice to differentiate? You're not going to get ugly fractions and minus 2 powers and, you know, just having to deal with that whole thing. So, yeah, I guess it's 3 and the quotient rule, but it's, you know, just because I could have used the quotient rule here doesn't mean I should, right? I've just postponed it a little bit, so I've got a nicer looking question. And I think this is a good point for you to say hi. And I will try and figure out what the heck Zoom is doing. And I think I might end up having just to do attendance every day, so I don't have that issue that I had last time. So say hi and bye-bye. If you haven't got your grade back, will you shoot me an email? Because obviously the email I'm using ain't working. I think by now everybody's fixed that, but who knows, there might be one person who hasn't. That's us.
Have you sent out the correct answers yet?
No, I have one person who's taking the test today, and then once that's done, I can do the answers.
Bye-bye.
I
Thank
do
you so
have
much
the
for the
answers,
great-
Teresa.
Thank you.
If you shoot me an email, I can send you the PDF version.
Oh, okay, good. Mhm. I will.
I'll wait
Thank you.
until, you're welcome. I'll wait until the person who's to do the test is done.
Yeah, that sounds good. Okay.
I just have a question with one of the questions we just did.
Yes, which one?
It was, you wrote down it's question number 20. It was the y equals e to the x plus x over e to the x minus x. Maybe it was that one, maybe.
Well, that's
Oh,
20,
wait,
but
no,
it's
no,
not
no.
that one.
Sorry, 20. It was y equals z to the 6 plus e to the z square root.
Right.
It was that
Did you say Z there? You know it's Z.
z.
Yes, right.
E.
Just remember to pronounce it properly.
Does it matter? Is there a difference?
No, I'm giving you a hard time.
Okay.
Good.
I got stuck because you were simplifying it and everything,
Right.
and then you got see, it was let me see, 1 2 3 4th line. I got confused where you underlined
Here?
6z to the, is that 11 over 2?
Yes.
How'd you get 11 over 2?
5.5 converted into a top-heavy fraction,
Oh, you distributed z to the 1/2.
and then combined them into a single fraction rather than a mixed fraction.
Gotcha.
Americans call them improper, but in Britain we call them a top-heavy. So 11.5 is essentially the same thing as 5.5. But
Oh, I
nobody
see
writes z to the power of 5.5. It kind of looks clunky if you do. So we typically call them 11.5.
Sweet. Okay. Thank you so much.
Okay, that was a short one. Okay.